This is module 3.3.1. In this module, we'll be discussing phosphorus. And phosphorus is important, much like our nitrogen and our sulfur. If you remember that the numbers on the bag are N, P2O5, and K2O. So we want to talk about those and some of the roles that phosphorus plays in our crop production. So you might remember back from plant science, where one of the outputs of glycolysis or respiration is actually ATP. And that is where we get the energy for our plants. That is what kind of drives all of the cycles. We need ATP in order to create energy to perform whatever functions that we need to function. It's important for protein synthesis and then also for this phospholipid bilayer. You remember that from biology? That phospholipid bilayer that kind of holds our cells together. It does play a small role in photosynthesis and nitrogen fixation, but for the most part, it's important for flowering and fruiting and seed production and root growth. And so we want to make sure that our plants have enough phosphorus in the beginning of the growing season because we want them to establish a healthy root system that can then scavenge the soil and get the other nutrients that it needs. And so if you have poor root growth in the very beginning of your season, you're not going to have a very productive yield. So phosphorus in the plant is mobile, but it is not mobile in the soil. It is held by those inner sphere complexes and makes it very difficult to be desorbed from those complexes and be taken up by the plant. And so much like nitrogen, you will see the deficiency in the older leaves. And you see this at the edge of this leaf, and it's purple. And typically, purple color leads me to believe there's a phosphorus deficiency. So purple and phosphorus go together. So some of the major problems that we have with that is like there's not a whole lot of phosphorus in our soils, just in general, like to start with. And most of it is highly insoluble and therefore not plant available. So what we want to do is we want to apply soluble fertilizers that can be taken up by the plant. But one of the issues is they can be quickly fixed and become unavailable because of those inner sphere complexes. The major problem that we have with phosphorus is water quality degradation and eutrophication. And so as we start to lose some of this phosphorus, it's not that the phosphorus is actually leaving. If you remember from the nitrogen module that we talked about, that nitrogen is water soluble, and so it can be kind of dissolved in that water and be transported with the water. Our phosphorus problems are actually coming from soil loss, because remember that soil is the primary polluter of our waterways, and once that soil makes it to the water, there are going to be some changes and some transformations, and that phosphorus is then desorbed off of those soil colloids and then introduced into the water system. So it's important to keep our soils on our property, or at least on our production systems, so that we don't, A, lose our phosphorus and our soil, and that B, that we're not polluting our waterways. This is a big issue in animal production wastes. And so our concentrated animal feeding operations, EPA is always going to focus on those. Because you're pretty much all the phosphorus that is in that manure that did not get absorbed by the animal is then going to be put somewhere and that is likely to be subject to some either leaching or runoff. And one of the things that my major professor used to say, and you might hear this again, is that the solution to pollution is dilution. And so they'll kind of put those animal waste products somewhere in a lagoon, hoping to dilute the phosphorus concentration before it makes its way into the watershed. And so one of the major, kind of important things that I saw here was that 10,000 head of cattle produces enough waste similar to the size of Murfreesboro. But that's a lot of people. That's a lot of waste. It's almost a whole town. And so, this will cause those algal blooms and Pfiesteria. So there's going to be some EPA issues when we start talking about gases and killing some things. All right, so we have two plant-available forms of phosphorus. We have H2PO4, and that is primarily going to be the most available, that's going to be the primary plant-available form when the pH is between about 4.5 and 6.5. We can see this on this diagram. And the other one is HPO4 2 negative. And so we can see that part on this diagram as well. And so right in between, when our pH is about 7.2, we have reached an equilibrium where we have equal amounts of H2PO4 negative and HPO4 2 negative. So that's kind of the equilibrium point. And so, as I mentioned before, that phosphorus is, held tightly to the soil colloids through intersphere complexes. Remember, that's with covalent bonds, so it's very difficult to break. And this is where the microorganisms come in, and we talked about those mycorrhiza. We have endo and ectomycorrhiza. And those mycorrhiza form that symbiotic relationship, and that mycorrhiza is able to extract or desorb these phosphorus molecules off of the soil colloids, and then kind of as a straw put them into the plant so that the plant can use them. So one way, if you have a phosphorus deficiency, one thing that you can do is you can add these mycorrhiza that will kind of improve your phosphorus uptake. Okay, so moving into the phosphorus cycle, again, we're going to have phosphorus that is in our residues because plants are going to take up phosphorus. Those residues need to be decomposed, so we have organic phosphorus that can then be mineralized into plant available or inorganic phosphorus that can be taken up by the plant. Here we are again. These three components are a part of every cycle. So you're at least going to get 3 of these right on the exam for each one of these cycles. Plant uptake, immobilization, and mineralization. Next, we have adsorbed phosphorus, adsorbed P. So remember, it's held to the soil colloid. It's actually held also to the anion exchange capacity. You don't really need to know so much about these transformations back and forth, but it is going to be adsorbed and desorbed. This is the anion exchange that we're talking about. So we have adsorbed phosphorus. It can bind with some of the other minerals in the soil to form these secondary phosphorus minerals. And if it's as calcium phosphate, then it's not being taken up by the plant. And so in order for calcium phosphate to become, soluble or, dissolve, we need to change the pH. So instead of, you would probably find calcium phosphate at more alkaline pHs because we apply lime. Lime, some of that calcium binds with that phosphorus to form calcium phosphate. The only way to break that or to decompose or dissolve that mineral is to decrease the pH so that it then, breaks apart, decomposes, dissolves, however, and then that phosphorus is potentially available to the plant. And then finally, we have primary phosphorus minerals. As I mentioned, those are going to be calcium phosphates that are like they're already a part of the soil as like that parent material. Those calcium phosphates are part of a mineral that was broken down from the rock cycle possibly, and that will then dissolve and become available to the plant. So the phosphorus cycle is even easier than any of the other ones. And then finally, we have runoff or erosion and crop removal. So that's how the phosphorus gets off of our property or our farm production system in our field. And so we need to be aware of how much how much erosion or how much runoff that we have, how much phosphorus was removed from the crop, and then how much is left in the soil. And so this is where soil sampling really comes into play. Okay, so one of the main differences between phosphorus and nitrogen and sulfur is that it does not volatilize. So we do not have any atmospheric volatilization, which makes that, that's a little bit better, right? We don't want to have any volatilization into the atmosphere. That's what we breathe. But remember that we do have this problem where we have eutrophication in our waterways. If you remember from from module 3.1, we have our superphosphates, we have MAP, monoammonium phosphate, and diammonium phosphate. These are going to be the primary phosphorus fertilizers, and having an understanding of how those actually break down in the soil to become available to the plant are going to help us manage some of these losses. I'm not really going to get into organic phosphorus as far as what those are, but it is important to understand that we do have this carbon to phosphorus ratio, just like we have a carbon to nitrogen ratio where we have immobilization and mineralization, and that our altasols and oxasols are actually going to have a lot of high organic phosphorus because remember we have intersphere complexes, and those intersphere complexes are going to be even more in our highly weathered soils because there's nothing left there's no more minerals left. And so phosphorus is going to bind and kind of solve the issue that those charges are looking for. They're going to bring balance. In our mollisols and vertisols, we'll have a lot of inorganic phosphorus, and this inorganic P is insoluble, so it doesn't really, contribute to plant nutrition. So it needs to undergo some changes and some processes, some transformations in order to become soluble. But, this is a high clay soil. It's got a high CEC and probably even a high anion exchange capacity. Mollisols are dark soils. They're going to have enough organic matter that is going to hold on to that phosphorus. We have acidic soils will have low solubility because as our soils become more acidic, technically, if you think about it, they're also becoming more positive. And H2PO4 negative is going to want to find a positive just like nitrate is going to want to find a positive. And so if we have alkaline soils, we have a lot of hydroxyls or OH negative. And so that H2PO4 negative is going to be looking for that positive. Also, we're going to have some calcium in there, and so that solubility will start to break those up, break those bonds as we start to have that dissolution and precipitation, and it can become more plant available. Remember that 7.2 is where we have both forms of plant available phosphorus. All right, so we have our different inorganic phosphorus compounds. We have apatite, and so apatite is kind of like the base phosphorus molecule or mineral that we use in order to make these calcium phosphates or MAP or DAP or whichever. So we do have some of these compounds that are minerals that are in the soil, and that as the pH decreases, this calcium phosphate is going to become more available. Again, when we say that as the pH decreases, we're looking somewhere between 6.5, maybe 6.75 and 7.5, because remember that medium is 7.2. So we want this to be about neutral so that we're not having any of the chemical reactions that are going to take place with making that H3PO4 2 negative. For our aluminum and iron hydroxy phosphates, so stringite is for iron phosphate. And the way that I remember this is that this E and the E in iron is stringite. And variscite. And the A in variscite and the Al in phosphate. I'm sorry, the Al in aluminum. Again, phosphorus is highly dictated by the pH of the soil, whether it's acidic or alkaline. So it's just something to be aware of, that as you change the pH, you're also going to be changing the solubility of these inorganic phosphorus compounds. And so I think that's when we go into soil fertility, when we start talking a little bit more about what happens when you do X, what happens to Y. And also, why does that happen? Again, we form those outer sphere complexes. Lime is going to increase that hydroxyl concentration, which is going to influence how much fixation or reaction that we're going to have in order to form those different minerals that are going to end up not likely being plant available. So phosphorus wants to be with these secondary and primary minerals, and that is where it's stabilized and at equilibrium. So we actually have to manipulate the environment in order to get that phosphorus to be plant available. Nope, none of that stuff. So again, we're back to soil pH, and remember that at 7.2, that is where we're going to, at 7.2 is where we're going to have equal amounts. We're likely going to have, they're likely dissolved, and they're more soluble and plant available, and they're not fixed to the soil. The ways that we can, kind of manage that is to make sure our 4R nutrient stewardship also applies to phosphorus, and that we want to make sure that we're applying the right rate, making sure that we're applying it in the right place. We want to put a subsurface banded application of soluble phosphorus right next to the root zone. We don't want our roots to have to try and force or to try and seek out that phosphorus, because it's held tightly to the soil. It's bound in secondary and primary minerals, and we can't change the pH enough in a number of those places in order to make that phosphorus soluble. So just being aware of some of the things that go on in the soil and what you can do in order to minimize that phosphorus deficiency. Some other things that you can do, we can have organic matter, managing our pH. These mycorrhiza are going to be huge. If you're having a phosphorus problem, consider putting some mycorrhizal application in your field. And then we want to obviously minimize the runoff and sediment losses, and we want to make sure that we have something like a buffer strip that will capture some of that excessive phosphorus before it enters our streams. Cover crops would be sufficient as well. Okay, so that ends module 3.3.1. You should be able to complete. Oh. All right, so that ends module 3.3.1 on phosphorus. We only have one more module left, and that's going to be a very quick one. It's the potassium and the micronutrients, and these are just making sure that we're touching on that. And we'll see you in the next module.